Welcome to this video. I'm Davis Montenegro and I'm the creator of OpenDSS-G. Today I want to talk about meters and monitors in DSS-G. So in the previous versions of OpenDSS-G, this is versions earlier than version 6, we used to describe data, transform data into information using a graphical interpretation or a graphical form for meters and monitors. This was a very simplistic way to present data, trying to mimic the front panel of a physical meter on an instrumentation panel. It was fun but not very practical because the data sometimes was very small depending on the monitor resolution, and in the end the user will be forced to export his data into an Excel file to be able to work with it. We had several representations in that version of the monitors and meters, but still it was not enough. So we tried to solve that by bringing something more dynamic in which we don't tell the user how the data should look like, but instead providing the tools for users to create their own instrument panels using graphical forms in OpenDSS-G. For that, we are introducing the DSS Widgets technology into OpenDSS-G version 6, which is what we're going to demonstrate in this video. Let's start the demonstration with a simple test case. Let's pick the Flisser test case provided with the platform that is based on the IEEE 123 node test case. In this one, we have several switches, we have some connections to adjacent feeders represented as voltage sources, and also some PV panels. This example also comes with several monitors. What I'm opening right now is the meter manager, which allows me to see all the different monitors and energy meters that exist in the circuit model. By right-clicking on the screen, I can get access to different options like, for example, shortcuts for creating new monitors, energy meters, location tools that allow me to locate the selected meter or monitor on the GUI. Every time I choose to see or to locate those on the GUI, they will blink on the screen showing me where they are located on the schematic. The user can also export or clear every monitor individually or collectively, depending on what is necessary. Other options allow to locate monitors per name, but the one that I want to show today refers to the environment. In this one, I can modify the appearance of the screen and the elements displayed on the screen, as well as save the settings that I've created dynamically. So every time you double-click on one meter or a monitor, you'll see that a new window opens displaying the data that is within the element, also describing the channels, the element that's being monitored, the type of meter that we have, if it is a monitor or an energy meter, and the operational mode. Right now we don't have much data, so what we're going to do is we're going to feed some data into it. We're going to change the simulation mode from snapshot to daily, and we're going to run a daily simulation. For that, I've just used the configuration panel. We can see that we completed a whole day. And now when I open my monitor, we can see that the data is there. Now the data can be operated directly, but let's go part by part. So we have the data in this table. We also have all the different components of the meter that will describe what the meter is about, what is being monitored, and what mode the monitor is in the case of monitors. Also in the window title, you will find the name of the monitor or energy meter. And every time we click on one of the channels, this will be highlighted and brought up into the table for the user to see. So we can easily navigate through the different columns and channels that the meter or monitor has. We can also, by right-clicking on it, right-clicking on the data, being able to copy it to the clipboard or export it to Excel, we can export the selected column or the whole table. In this case, I'm going to export the whole table to the clipboard, and just by clicking on Ctrl+V, I can just paste the data and get it on Notepad, for example. We can do exactly the same with Excel. So in this case, I'm going to select the option Export to Excel, the whole table, and we're getting everything immediately exported to Excel, so we can operate over it and, well, do some calculations if needed. And then the other option that we can explore is to add widgets. We have several widgets like meters, polar graphs, we have state of charge, we have waveforms, we have harmonics, we have QSTS, and other options for saving the data that we have or the widgets that we have created for the specific monitor we're working on. Let's start with one of the widgets. Let's start with the meter. In this case, the meter allows us to monitor just one channel. So let's select, for example, the voltage in phase 1, and then click on apply, and there is our widget. Now the cool thing is that every time you sweep or select the data from the table, the widget is gonna be updated. So you can basically go up and down to the data and the widget will be updated. If you run another simulation, the widget will automatically update. Now the name of the widget will match the name of the meter it was derived from, plus a number just to differentiate it from other widgets. The other widget that we can create is the polar graph. In this case, we have to create data pairs for representing the magnitude and phase angle of each one of the vectors of the polar graph. In this case, just drag and drop each one of the components. For example, in this case, I'm trying to build a polar plot for voltages. If you want to delete one of the components, you can do it and then start over. Just as I showed on the screen, you will see that every time we create a pair, the channel will be checked to the left of this little panel. And once we click and create, the polar plot has been created. This one is resizable. The meter is not resizable, but this one is resizable and will show you the data numerically on the vectors if you want or not. Now, another cool thing that widgets have is that they allow you to align widgets of the same type. So let's create another polar plot, but for the currents. Let's bring the currents here. So we're going to bring magnitudes and angles for each one of the phases, and we're going to create it. So right now, the plot is created with no format, and when we aligned, it will match the size and get right next to the widget that commanded the alignment, making it super easy to organize the front panel. And when you just move around the data within the table, you will see that every widget will react to this action, making it super easy to navigate the data. Similarly, the state of charge widget will allow you to see the instantaneous value. Let's say that this state of charge is more like a tank representation of the data, and ideally should be used for representing the state of charge of a battery, but since we don't have any here, we're gonna use just one of the voltage phases to represent the data. We can see that the widget gets updated automatically, but we're gonna close it because, well, it's not adequate for this simulation. The next widget is the QSTS. This one brings the whole content of the monitor or energy meter, and we have all the channels active, each one highlighted with a different color, which matches the curve that they're representing. By right-clicking on the list, we can deactivate everything, and by double-clicking on the channels we want to see, just bring into the graph the ones that I want to see. In this example, we're bringing the currents per phase recorded by the monitor. Every time I move through the data within the table, you will see that the cursor will show you within the QSTS graph where that data is located. Also, I can grab the cursor and synchronize everything within the monitor with the data that we're displaying to the QSTS monitor. This one is resizable, and you can select at any time what type of data you want to see. Do you have other tools within this widget that allows you to zoom in, zoom out, pan, etc. This to provide a quick visualization of the data that is contained within the meter. If we bring another monitor, we can easily launch another QSTS. For example, this one is another monitor. Let's see the currents in that area of the feeder. We can see that the curves are quite different. But the cool thing is that you can bring everything to the same time instant just by right-clicking and selecting the right option from one of the widgets. You can synchronize the entire environment just to reflect what you're trying to see. We can hide the meters, the monitors, if I want to just see the widgets. And also, if required, we can hide and bring back all the widgets across the screen, just in case, for example, we're working with just one monitor and we need to get back to the simulation and then see what the results of the simulation or latest actions were. We can at any time bring back the monitors just by clicking on those. They're just minimized and available within the icon of OpenDSS-G. Every time we close one of the monitors, this one will close all the widgets that we have available for it. Let's suppose the following. I'm gonna save the whole environment or all the widgets created for one monitor and try to bring those for another one of the same type. I can do this as shown in the screen, and this will replicate and bring all the different widgets that we initially created for one monitor and reuse those definitions for launching the same type of widgets on a monitor that is compatible with them. For the next demonstration, I'm going to bring the IEEE 123 node test system, and I'm going to demonstrate some other widgets. In this case, I'm going to use dynamic simulations for that purpose. What I'm going to do is I'm going to use the DSS-G scripting panel for adding a storage device and a PV system. Then what we're going to do is we're going to open one of the switches of the 123 bus test system, and we're going to operate the system as a microgrid. So there's one part of the system that's going to be fed by the PV system and storage cell. Right now I'm just commenting out some lines that come from the original script in order to make it comparable with my implementation in OpenDSS-G. With this, I'm going to enable simulation, run the simulation, and voila, we have everything. So we have finished the dynamic simulation. We have some monitors created through the script. We can see that we have monitors for power and voltages and state variables for both the PV and storage. Here I'm showing the switches that are installed in the system. We can see the one that's open. Also, let me illustrate where the PV system and storage are located using the visualization panel. So now what we're going to do is, after running the dynamic simulation with a time step resolution of 1 millisecond, to extract the behavioral variables to evaluate the performance of the black start operation when the storage device is set up to operate in grid former inverter control mode. Let's start with the power measurements. So for that, I'm going to bring the monitor monitoring the power coming out of the storage, and we're going to create a widget called QSTS. You've seen this one before, and it will reveal the way everything happened for the storage when creating the microgrid. We can see that the active power was initially very high when starting the microgrid, kind of black starting the microgrid, and then it went down because of the entrance of the PV system. So the PV system evaluates if the voltage conditions at the terminals are correct, are adequate, and then starts generating. That's why we're seeing this behavior here. So we have two different dynamics, the storage dynamics and the PV dynamics. How does it look like in terms of voltage and current for the storage device? For that, I'm going to create a waveform widget. The first one will be pointing to the voltages of the storage device, and here we can see the exponential increase of voltage at the terminals of the storage device, which is the one that's serving as reference for the microgrid. In terms of current, we can do the same evaluation. As you can see, the waveform widget recreates the sinusoidal waveforms for whatever variable you're putting in based on the phasors provided by the OpenDSS simulation. For instance, the current waveform matches with the power QSTS widget that is basically telling us of the peak demand at the beginning of the black start. Then we will see how the current basically gets lower given the entrance of the PV system. The interesting thing about these representations is that you can have a very good approximation of how the waveforms will look like in the time domain using a frequency domain simulation like the one that happens in OpenDSS. To demonstrate this widget better, let's do something crazy here. Let's add a load to the microgrid so the storage device is not able to pick up, and with that cancel the black start. For that, I'm removing also the amp limits. Let's see what we got after opening the monitors. So after the simulation runs, I'm gonna open the power monitor that we had for the storage, and I'm gonna represent the power as a QSTS. Here we can see that the active power was initially delivered, but then when the storage device realizes that cannot pick up that load, it basically cancels the black start and starts turning off. From the waveform point of view, in terms of voltages, we can see the analog representation of the vectors informing us on how the black start was canceled, given that the storage device was not able to catch up with the load within the microgrid. Some other widgets are very specialized, like the Harmonics widget. In this case, I'm bringing this test case that is included with the platform, and is an example that is provided by the IEEE 519 standard. In this one, we have some linear and nonlinear loads, and we're measuring the harmonic distortion at the point of common coupling. What I'm doing right now is changing the simulation mode to harmonic to see how it behaves. Once we open the meter manager, we can see the location of the monitor, which is right up there at the point of common coupling. So what we're seeing in the simulation, the data captured by the monitor reveals the effects on voltage and current harmonics when connecting all these linear and nonlinear loads together. To visualize it, first I'm going to create a harmonics widget using the current's magnitude. Once I launch the widget, I can see the different harmonics per phase depending on the channels that I've decided to include in the widget. In the simulation, I'm separating some nonlinear loads to see the effects on the current harmonics at the point of common coupling. Also, can add other widgets like, for example, the waveform that will translate the spectrum measured for the variables that I have selected, representing them in the time domain. Every time I change a variable or I change a component within the simulation, the widgets are going to get updated. For example, if I keep opening switches, we will see how the spectrum and the representation of the spectrum in the time domain will change and update accordingly. After creating all these widgets and setting up your graphical environment, the user can save the whole environment in order to be reused in the future. Like, for example, instead of just creating the environment and having to recreate everything again the next time you use the system, we can save that using a very interesting functionality included in OpenDSS-G version 6. To save the graphical environment, right-click on the Meter Manager and select the option Save to File. I'm going to create my environment 3 and save it. Now, to show how it works, I'm going to restart the whole system. Here I'm launching my system again, and after enabling the simulation, I'm going to go to the meter section and select Load from File for the environment. Then select the file that I just created, and that will bring back the whole graphical environment. From here, you can start simulating, and the environment will respond to the simulation, updating everything like if you never left. To learn more about these and other functionalities, check the user manual. This is available and up to date with the software. In fact, we have a specific section called Monitors and Meters that describes the ways for creating monitors, meters, how to operate and what it means to have a meter open, how to operate in all the different functionalities that are included in the Meter Manager, as well as each one of the widgets described individually. I hope you have enjoyed this video as much as I did. Thank you.